Start up, everybody. Well, hi, everybody, and welcome to our presentation of SCNZ on Vision to Reality, the University of Auckland Recreation Centre. I'd like to thank you all for joining. I know everyone's busy, or we really hope that you're really busy, because if you're busy, structural steel is going to be busy in a few months' time, hopefully. But thank you for joining us. First of all, my name's Darren O'Reilly. I'm the General Manager of SCNZ Steel Construction New Zealand. And I'd like to thank you all for the opportunity to speak to you. You might not know who SCNZ is. For those who don't, SCNZ is the structural steel industry body. We like to sort of flatter ourselves that we're like the master builders for structural steel. We have about 700 company members, and we've been in existence for coming up to 20 years. Most of our members, consist of those who manufacture structural steel and steel products, and right through to distributors, fabricators, designers, detailers, erectors, steel coaters, and all those who are involved in the supply chain of the steel. So we are the voice of the structural steel industry in New Zealand. And you can see our website there on screen. It's pretty easy, www.scnz.org. Most of our information is free, so please feel free to hop on there and you can see a lot about what we do and who we represent. But one things we're really big on is actually sharing knowledge amongst our membership in the wider construction industry. To that point, it's my pleasure today to introduce our two note speakers, Tony Dew from Warren and Marnie, and Richard Hine from D&H Steel Construction. Tony is an associate and project lead with Warren and Marnie. Tony has extensive experience with delivering high quality outcomes across a broad range of sectors. Tony is passionate about seeing projects through the initial concept to final completion, ensuring design intent is carried through every stage of documentation and delivery. Recently, Tony has led the technical delivery of the award-winning Hiwa Recreation Centre for the University of Auckland, a project that truly exemplifies his commitment to excellence and a collaboration approach to achieving the best outcome for the clients and communities. Now, Richard is the General Manager of D&H Steel Construction. Richard is a qualified structural engineer with extensive project engineering and management experience, having successfully delivered multi-million-dollar projects in Hong Kong and Dubai and other parts of the world. He brought his international experience back to New Zealand, joining D&H Steel as contracts manager. After 5 years, in 2020, he was appointed as general manager. Since then, Richard has overseen the successful delivery of tens of thousands of tonnes of structural steel projects throughout New Zealand. His project portfolio spans a wide range of projects, both in New Zealand and overseas, including multi-storey commercial buildings, shopping malls, transport hubs and industrial warehouses, and many other large-scale commercial projects. And Richard is actually the newly elected to the SCNZ board, so he's well respected amongst our industry. So without further ado, Tony and Richard, the floor is yours. But just if you want to ask a question during the webinar, just please post it online at the question and answer ability to put a post on. So Richard, Tony, over to you.
Welcome everyone.
Thanks Darren, that's a lovely introduction.
I'm Tony and this is Richard.
I'm Richard.
And I will just find our presentation. So thank you all for letting me present this great project. It was a 6-year journey for me from when I started at pretty much PD to the end of the project in sort of last year. For those people out of Auckland who are not quite sure where the project is, so this is the Auckland campus, central campus. You see in the middle of the screen here is pretty much where the old rec centre was. We demolished that and have built in the same space. The old quad is still remaining there. Student buildings are over in this hub. It is pretty much a central part of the campus. Just a bit of the timeline. So we won the RFP in 2017. It took us a couple of years to get documentation together. And then 2019, you can see there, D&H were engaged as part of that early documentation to help the process.
Maybe I just mentioned there's something that was a bit unique with this project is we were engaged directly by the University of Auckland rather than the main contractor Hawkins. So the reason for that was some early subcontractor involvement that we could work with WAM and Becker on developing the design before they'd gone too far. So we were involved in 2019 and then got novated over to Hawkins, the main contractor, about a year later.
Yep, we can see that there, 2020, novation across, first steel orders were put in. 2021, we started the journey on site. 2023, the last of the steel superstructure was completed, and then the project came to an end towards the end of 2024, and building was pretty much handed over to the university for the start of 2025. Just a few fun facts. So on the right side there, it's about 40,000 students at the university. Probably about a month after we opened, they saw 5,000 students come through the gates in the first weeks. The GFA, 21,600. That's over 9 levels. The pool tank, which was one of the interesting parts, it's a 34 by 20 metre pool tank. Stainless steel, so the whole pool was fabricated stainless steel. The show court has also 15,000 seats, 1,500 seats. That show court has a glass floor to allow LED lights to show the court lines, and then we have a second court, which is we call the practice court, which is more traditional timber floor. And then some tidbits for Richard.
Yeah, I mean, it was clearly a pretty impressive structural steel project. I remember this morning, and I didn't put this up here, that the average weight of a piece of steel that was erected on this project was a tonne. And so that's well off the normal metrics. But on top of that, there was about 6,000 tonnes of fabricated steel in this project, all fabricated at D&H in Auckland. 85,000 structural bolts went in to put all the connections together on site. Obviously, a lot of site welding as well, which I'll get into a bit later. There was 200,000 hours of labour put into this job by D&H employees and staff. To give you a bit of an idea of what that means, that is 50 people working full-time for 2 years to deliver this project. So that's the fabrication, the shop drawings, the erection on site, and some admin side of it. Put a bit of a structural loading in here. I won't talk too much about structural loads, but there was 15,000 kilonewtons was the maximum load that was supported by one of these diagrid members, which we'll show you some pictures of later. That's about 1,500 tonnes, and to put it in layman's language, that's 75 double-decker buses stacked on top of each other. At least that's what ChatGPT told me the other day. The heaviest assembly to be erected on site was around about 40 tonnes. That's a big sports hall truss that supported the roof of the sports hall. They were about 36 metres long and about 5.5 metres deep, and needed 2 cranes to lift them up simultaneously. And then the longest member that was delivered to site was 30 metres, which is pretty unique. And again, I'll talk about that a bit later on in the presentation.
Thanks.
We've got a little freeze on our presentation.
Stuck. Classic.
Slight technical difficulty.
Yeah.
Here we go. We can use the mouse instead.
So here's just a little bit of a snap of a quote. I'm not quite sure, to be honest, where this quote came from, but it just, the main highlighted words there are pretty much what drove the design here. How can we connect, unify, enhance, and maximise, more importantly, the student wellbeing? And that was pretty much the driver for the whole project. Now I'll just dive into some more design drivers. Obviously, massing, the visual connectivity from Simon Street up to Princess Street at ground level was very important. Then moving across, just enhancing those connections and the edges, and obviously the surrounding buildings. And then most important for the students is just the circulation and public access from Simon Street up Princess Street to Albert Park. Obviously we had some height controls, and then because of that huge program that we had, just trying to fit all of the wishes of the university, we decided to lift the show courts off the ground, and I'll go into a bit more further along why that happened. Again, optimising the height restriction lines and a few other things. We split the show court. There was some other internal reasoning behind that. Then the formal facade. So here you can get to see why the diagram came about. So from those initial ones around the edge treatment and the visibility, you can see how that massing is starting to come through. And then finally, down in the main corner of Simon Street, clear address of the entrance point. Oh, yep. Now into some of the planning quickly, design planning. So this is the lower level, so B2. This is actually underneath the pool concourse, so you can't quite see that, but that is the stainless steel pool and the buttressing that holds the pool. We have full access around the pool, obviously for maintenance and just general. We hopefully move. Yeah, so this is the pool concourse level, B1. It's pretty much the main access. So you can see the pool with a full concourse around it. To the left is a 4-metre deep diving area. Where the one is a 2-metre main swimming lane, and then to the right we have a 3-metre deep movable floor that can come up above the waterline. That's in competition mode, so that all the judging and staging can happen at the end of the pool. And then obviously you lower the pool to whatever height, the floor to whatever height you require for aqua aerobics, water polo, and a few other things happening down that end. You can see number 2, that is the spa, student spa. And then up the top of the page is more the changing rooms, back of house. Number 6 to the far right there is 3 squash courts, and then the bottom of the page is some back of house car parking and filter areas, electrical, back of house stuff. Moving up, so this is our access from Simon Street. So you enter in on the right there, number 1, and you either head down the ramp to the reception point and the secure entrance into the facility, or you head up the page to the atrium area, which is a free public access. You'll see a bit more of that. Top of the page is again back of house office areas. And then at the bottom of the page is where we start our first parts of the program. Number 3 to the right bottom is the heavy weights and weights area. And to the left is some changing facilities. Up one more level, so this is above ground now. So you can see the 1 is the atrium space that has the connection for free public access that moves through the building up to 13, which is an entrance point, and then out to the plaza to the far left. You kind of come up a kind of a half level to our first of the aerobic area. So this is an aerobic floor. Number 2 in the middle there is cardio. And then the areas to the bottom are the sort of the gym, workout, CrossFit. Bottom of the page, number 8 in the middle there is a spin class. Number 7 next to it to the left is boxing. Now we move up to our show court. So to the left is the show court. At the moment, we've got some lines there showing a few games going on. At the top of the page, we have 1 and 2, which are our mind, body, and soul. So we have a dance class and a yoga left and right. In the middle is changing rooms. So this area in the middle was the main circulation area and seen as where the students would hang out. So there's table tennis tables, a climbing wall or bouldering wall, and just before I dive into it, so the idea of that splitting of the 2 sports halls was to gain circulation in the middle of the building. That circulation was also seen to be part of the wellbeing part. So we have a running track that starts from ground floor, runs through the building, up the stairs to the roof and around the roof. It's about full circuit is about 1.2k. Then on the far right is kind of the half floor in the sports hall, and again running track around that. And then number 6 is our practice court on the floor, which can be divided up. Number 1 on the left is plant room that sits above the sports hall. And that repeats to the right. And then the blue area is the turf court. All of the images to the far left sort of reflect the finer photos of what's happened on site. A bit more of the roof. So level 5 is the bottom blue part with the tennis courts and futsal. And then the top is another running track, free area on the level 6. Bit of a cross section through the building to show you the activation. So again, left you can just see the buttress of the swimming pool, and then on the right, slicing through the building as you move your way up. Number 6 there is the sports hall 1 sliced. 7 is the plant room. 8 is the turf floor above. Now I'll sort of hand over to Richard, who can talk about the beautiful structural strategy. So again, that top photo on the left there is, it was very much a design idea to have exposed structure. So it's always been part of the design to bring out that beautiful diagrid.
Thanks, Tony. So yeah, I'm going to talk really through sort of 3 main parts, sort of features of the project, being these diagrids and mega braces. I'm going to talk later about the long span trusses that supported the roofs to the sports hall, and then also Tony mentioned about the aquatic centre pool and the roof structure to that, all of which, just thinking, were in parts or mostly visible sort of structures. So they all had quite a lot of focus around achieving the architectural vision. So I'll start with this diagrid and mega braces. We didn't use the word mega braces lightly. These were the members I mentioned before that were supporting, 75 double-decker buses worth of load coming down each of these diagrid members. That'll be under a seismic event. So these mega braces are sort of a dual function. They are columns that are supporting the overall structure in the sports hall floors, but they are also the load resisting system for seismic and wind. But as Tony would say, they probably more importantly are visually dominant. And he talked about clear address before, and these are the structures that as you walk up to the building, and that picture up the top left there isn't an architectural image. That's a real photo of the finished structure. So you can see the public get up very close and personal to these diagrid members. So we were engaged on an ECI, early contractor or early subcontractor process on this project, which entailed bi-weekly meetings, a lot with Becca to look at efficient sort of well-designed connection design, but also some with WAM to look at how we could go about practically achieving the visual intent. And so that involved a number of things, starting with these bottom nodes. So this is a node here. This is a piece of diagrid. I think hopefully you guys can see the pointer. This is a piece of diagrid sitting on a trailer getting ready to go to site. Up here, the same piece would be this piece here. And so a node was this bit at the bottom. And to give you a bit of an idea of scale, these holding down bolts here were about 4 meters long. And these holding down bolts assemblies alone weighed about 3 tons. So these nodes at the bottom here were where the public can walk around. So how they looked was hugely important. We spent a lot of time doing some preliminary modeling of these plates and their connections, because a lot of these plates, and they are starting from 100 mil thick, but many that were 60 or 50 mil thick, needed to have a smooth transition into these diagrid members here, partly for visual appearance, but obviously also we couldn't have any sharp edges down at this lower level here. So we did a lot of modeling early on, which included a little bit of unique modeling of special cuts in these plates that were these 60, 50 mil, 100 mil plates had special cuts modeled into them that were then done through plasma computer controlled cutting to achieve a nice smooth architectural finish here. Now, of course, coming out of the cutting lines and machines, there's still a bit of work to be done after that, and so there was a lot of grinding to be able to smooth off welds and that sort of thing. We went as far as doing a full-scale mock-up of a portion of this diagrid member here. So this diagrid member, I'll just explain a little bit. They are 800 and 900 millimeter square box sections. They're made up from four pieces of plate, four sections of plate for each wall that were welded together in our factory. And so that welding process itself had a lot of focus, mostly between us and Becca, on how we'd achieve the design strength they needed while maintaining efficiency in that weld. Many, many kilometers of weld, as you can imagine. But then achieving these nice smooth lines as well was hugely important. So we actually fabricated, I think it was about a 3 meter long piece of this diagrid. So we could run some trial samples of the welds that joined the plates together, make sure that was all compliant and achieving the strengths that Becca needed. But also we had WAM and the university and the project managers come out and inspect the finished quality. So they could see the kind of quality that we were going to achieve. We were pretty confident we could get what they were after, which is effectively invisible welds. And we had a couple of visits out to D&H to sort of view that, and we put the paint systems on as well. So we had a full scale sample of that diagrid sitting in our workshop, maybe at least a year, if not a year and a half, before we got into the main manufacture of this. Couple other points to talk about. So obviously these members are very heavy, and getting all the fabrication tolerances and weld design right was crucial. But to achieve a finished product, and this is effectively a monolithic structure. So all of this diagrid along each elevation, and in fact around the corner, is fully welded or bolted together. And what you can't see here, fortunately, is there was a number, or in fact, every one of these diagrids had a full penetration, so a full strength site weld being done on site, which to achieve the sharp finish lines on this and the very tight tolerances of fabrication and site installation, we actually manufactured, and you can see it on this bottom picture down here, at least a portion of it, We laid out on our workshop floor a full elevation of this, of each of the elevations of the diagrid, so that we could weld the full diagrid together with these nodes. Again, you start to see a bit of scale here when you've got 5 fabricators standing around one of these nodes. Gives you a bit of an idea of size. We fabricated a full elevation in the workshop floor, lying flat, got that all perfect. Then once we were happy with that, we cut this diagrid into sections. So we put a cut through here that broke it into around about 25-ton pieces that could be delivered to site. Once they were delivered on site, we had a fairly complex and highly engineered temporary work system that could hold these diagrid members in position so that the welds could be completed on site. And once these welds were completed, these were also ground flush and painted over. And as you can see, the finished product is you cannot see any welds there. Move on to the next part of the structure that I wanted to talk about. So sports halls. Tony mentioned before, these sports halls were lifted off the ground. That was mostly through that use of having that diagrid structure. But of course, the sports hall space is a large open space, and structural steel was the ideal material for that because it's extremely strong and surprisingly light for the amount of strength that it can handle. And so Becker designed these long span trusses. These are about 30 or 36 meters long. They're about 5.5 meters deep. The depth of that truss enabled a partial floor to be built on the lower chord of the truss, where most of the plant and services, if I remember right, could be positioned, which is out of sight in the building. And also the depth of that truss itself being 5.5 meters gave it some structural efficiency. So we spent a lot of time with Becker looking at all of these connection details here, how to design them most efficiently for cost and construction. What that ended up with is these trusses were fabricated in 3 pieces so that they could be delivered to site. There's obviously site logistics around getting into site and getting to site. Once they were delivered to site, we pre-assembled them on the concrete sports hall floor in the vertical position and used 2 of the tower cranes on site, or the 2 tower cranes on site, which were, I heard, the largest tower cranes in Auckland at the time, so they're not small. And through a tandem lift, which is when you can connect and lift up a member simultaneously, we lifted these 40-ton trusses into position, and there was 5 of these above each of the sports halls on either side of the building. There were big parts of these structures that were visible, which you can see some of it up here. So again, there was quite a lot of consideration about how these connections would look, how they would come together, a lot of discussion about methodology with all parties. Then the aquatic hall. So this, as Tony touched on earlier, was an underground pool, stainless steel pool. The roof structure here was hugely unique, partly because it was supporting what they called the plaza mound above, which was a sort of continuously curved structure that needed to support the load of vehicles coming over it, and obviously all the public. So the way that was done is these members here, which don't look very big in the model, and in fact don't look that big in situ on this picture down here, but when you look at the top right, you start to get an idea of scale. So these members were 30 meters long, and they had an ever-changing crank in them. So 30 meters long, but they cranked at about the halfway point so that they could follow the plaza mound shape that it was supporting above. And if that wasn't tricky enough, the member itself, just to give you an idea of size, is 1.2 meters deep and 0.4 meters wide. And again, in some ways not dissimilar to the diagrid. These were fabricated from 4 plates and welded together at the 4 corners. How they looked was, or how the finish and how they looked on site was important to WAM, because when you're doing backstroke in the pool and looking up, you can see these structures above you. So we spent quite a lot of time with WAM and Becca coming up with some efficient and aesthetically pleasing weld details to join the plates together. And I'll just explain that a little bit more. We did have to butt weld these together, but the amount of weld runs that we have to put into this really translates directly to the amount of cost of putting something of this together. And so through a collaboration with WAM and Becca, we managed to design a weld detail that required only 1 pass of weld, which is quite unique. And when I mean 1 pass, so 1 30-meter pass on each corner to complete that. And then what was important with that is we didn't need to do any post-weld cleaning or grinding of that weld to make it aesthetically pleasing because of the way that we detailed it. Now, if convincing WAM on paper wasn't good enough, we also produced a scale sample of one of these in our factory prior to getting into it. So we fabricated a few meter long piece of this and then invited WAM, the university, out to have a look. And we actually slung it up on one of our gantry cranes in the factory. This is our factory in the background here. We slung it up and pulled it up as high as we could on one of our gantry cranes so that Tony and the team could look at it from a actual on-site distance away to see if they were happy with how these members were going to look from underneath. Getting them to site, obviously hugely complex. This sort of setup that you can see in this picture is clearly not the normal way we would be delivering steel to site. This is called a Jenka trailer. And this trailer at the back has got a truck unit at the front and then a trailer at the back, which has its own driving power, and it can be remotely steered. So the wheels itself can turn, which is what allowed us to deliver these structures into the University of Auckland, which is, as you can imagine, not an easy path. It all had to be done in the early hours of the morning. So these were loaded up at our factory the day before onto this special trailer. And then starting at about 4 a.m. in the morning, they made their way towards the university, and then they were delivered into the project and taken off the road. Had to be off the road by 7 a.m. No compromise. So we were getting them there at about 6 a.m. and getting them off so that everything could be cleared by that 7 a.m. cutoff. There's a number of these that needed to be delivered. The other thing that was unique about this, and you can sort of see it from this model in this picture below, is every single one of these members is dimensionally unique, apart from the last few that are straight or flat. So this section through here is an ever-changing curve and pitch, which is quite a conundrum when it comes to modelling it. And so there was a lot of collaboration with WAM on using their model to get the finish profile of the plaza mound above. Then we know the structural makeup of that floor, which is a metal decking system with probably 150 from memory concrete floor slab that was needing to be curved to suit the shape. And we worked down from that to be able to model ourselves the position, the exact position or RL of all of these members here. There was, really quite special piece of collaboration there to get that right and make it work for the other trades as well. Like the metal decking doesn't curve well, so we had to come up with some unique details on how to support that metal decking and fix it down to the top of these members here so that the concrete could be poured onto it. It's probably about it from my side. Talk a bit about BIM collaboration. I don't know if you want to kick that off and then I jump into it, or?
Sure. I mean, quite clearly, very complex building for a commercial building. Normally hospitals are the most complex, but this one was highly complex. So collaboration from all consultants and even Hawkins itself with their own federated model was the biggest driver of getting things right on site. We quite clearly eliminated some huge amount of on-site issues by having models by everyone, so that we could preempt and get in front of any issues that we could foresee. So not only you can see in the top sort of left picture there, that is structural steel. Very hard to review shop drawings when you've got steel going in all directions. So this is the first project where we actually did our shop drawing review through 3D modelling.
And if I remember right, Tony, we set up a bit of a process on this project where we would work to get portions of the structural steel model completed, and then we allowed a bit of time in the program to pass that model over to WAM and to Becca, and gave them some time to review the model, make sure everything was in the right place, the connections were right, do a bit of clash detection, and really make sure that model was 100% right before we moved into a phase of doing shop drawings. So that's hugely time saving for us in the long run. It means we don't, less chance of rework after we've done our shop drawings, which takes a bit of extra effort and time. So we were breaking off parts of this model as we completed, passing it over to the consultants, and they had some time to just effectively do a model review before we got into shop drawings. And then when we did the shop drawings, we provided another model at that point with a set of PDF shop drawings. Again, another chance to check the model, do some clash detection, and then when we went to fabrication or for construction, we provided a third model. So it was really each part of the structure as we progressively, built it in the virtual space to building it in reality was, involved 3 separate models to get that completed.
It was a good process. So normally there are quite a few clashes, incidental things that we weren't prepared for that happen on site that could turn things in the wrong direction. But by having this model, and then on the right you can see we've put the architectural on top of that. You can clearly find out where we're going to have any issues or potentially need a bit more tolerance to be built into the envelope to allow for the structural connections. So the bolts and the plates and the cleats suddenly turn up and they were a lot bigger or different sizing that we weren't prepared for. We were quite clear that it became very apparent that we needed to adjust things. So very good process. It's a very good process actually. I've enjoyed doing shop drawings. Normally not the best.
The other thing I'll mention here is WAM provided us at the outset of the project their models of the full structure, and so to start getting into positioning the members, obviously we get size and connection detail from Becca, but the position of those members, we were using the WAM model to guide us on where to position those members. And you can imagine, whilst some of them are on grid, there was many hundreds or thousands that were not, that were unique for secondary steel, for services support, facade support, and rather than us trying to sort of start from scratch from the WAM drawings, and they'd done a huge amount of great work to start with, we were able to take their model and start building on that model to save some time in our modelling process.
So yes, BIM Revit is becoming a very important tool, and then the amount of modelling we actually do within that is starting to increase. And just the final picture of, so this is our practice court that you can see at the bottom left there. Again, that was just to highlight that we did see the beautiful work of this diagrid structure that we wanted to put on display. So it's a glass facade in those corners that you can see. And then we have internally a little bit of perforated metal just to allow for glare control. But you can see those beautiful diagrid connections there on display. And that's pretty much it. How are we doing for time? We didn't actually do a time check.
Good. I reckon you could show the time lapse.
Yeah, so before we jump into some questions, I do have a time lapse that shows the site under construction and beautifully goes through that steel manufacturer. Oh. So this is from the webcam that was on site. I didn't record it that well, so it sort of sends and then goes to the start. Here we go. So there's digging the hole, getting rid of the old rec centre, prepping the foundations for the steel to come. See, we started from north, headed south.
That's those sports hall trusses going up there. That last piece is the turf roof, which we didn't talk much about today.
Yeah, I guess we're just going back to those large spans. It's back to that. So we did not want in the visual sightlines to have any large plate connections, which is why we forced these guys to look at doing these large span deliveries so that we didn't have any gusset plates in the middle. We just had beautiful, clean, sharp beams, and we managed to achieve that everywhere, basically. So that turf roof, no gusset joins in the middle of the court. The trusses, obviously, we hid quite beautifully with some ceiling, but in the pool, again, no gussets there, just some beautiful, clean line beams. So, is there any questions? Oh,
can you hear me now? Yes.
Oh, yeah, there we go.
Yes, sorry. I do have some questions. The first one was, were there, and there was a couple of people who asked similar questions. Keep coming the questions through, people. We've got a bit of time. Were there any sustainability targets such as Green Star points targeted for this project?
Architecturally, no. So because of the material choices, and it was a request by the university not to do a Green Star, we did look at doing a WELS, but the WELS rating was more around the obviously, Warren and Marnie hold strong opinions and directives around being as sustainable as we can. So obviously we designed as hard as we could to achieve the best outcomes.
Maybe if I can just touch on steel part of that, given the chance. So yeah, we didn't have any Green Star targets that we were asked to achieve, but you know, these days, and this project is no different. Most of the raw steel that we procure in from offshore, which is all of the steel that's used on that project, is made from a manufacturing process called electric arc furnace, and so there'll be at least 80% recycled steel in that project. Probably some of the other things I'd say is, you know, the building's got a 50-year design life as part of the building standard, but you know, that structural steel will clearly last with little maintenance much longer than that. You know, 100 years plus wouldn't be a problem, and part of sustainability is what's the construction footprint to go and build it, and if you've got a building that lasts for a lot longer, the relativity of the construction sort of carbon and sustainability piece reduces, so that, you know, steel in a building like that will, and in fact any building will last for much longer than its design life. And then of course, when it eventually does have to be demolished, hopefully not in our lifetimes, that steel will go back into the melting pot and be recycled again for another project. So while we weren't put on any sustainability targets, you know, that project, like all of the projects we really do in New Zealand, do have, you know, generally lower carbon footprints to start with than a lot of the other projects around the world, and would have been made from well over 80% recycled steel.
It's good, and of course, as you say, it doesn't ever end up in landfill, which is brilliant. There's I guess the question it wasn't specified on who was asking, but in hindsight, would you have done anything different? So I'll start with you, Tony.
No, I think the process, material selections, and the outcome. There has been no real hard feedback back from the university on things that they could have done better. It's always a good test. Students are always the best people to test materials and your design philosophy. And we're certainly getting a few materials that are getting tested. So in terms of material selection, there may be some outcomes from that, but in terms of the design and what we managed to achieve in that space, I don't think there'd be too much tweaking.
If I had absolute power, I would have chosen not to build it during COVID. That was pretty challenging. And so probably a part of that whole, COVID life cycle and the construction boom that followed afterwards, trying to keep costs in check for the university. There was a lot of discussion around strategy on steel procurement. When would we order the raw steel from offshore? It's obviously a globally traded commodity that's, very market driven. And so we had a lot of talk with the university early on before COVID hit and that whole construction boom about delaying the purchasing of steel so we didn't have to store it, which came as a cost saving. But then the consequence of COVID and the liquidity that the government pumped into the construction in many sectors meant the world construction boomed. And so the price of steel really started to ramp up. So we were quickly trying to scramble to get the steel into New Zealand as quick as possible. We had lots of challenges with shipping, which got chaotic. So in hindsight, I would have bought the steel in a bit earlier because that would have saved a little bit of cost. But didn't know what was going to happen at the time, obviously.
Yeah, this project was a bit unique in the fact that we had so many world events. So obviously, Ukraine war had a little bit of effect on some of our materials. Suez Canal, when that got blocked, our cranes got stuck for a little while. We had COVID, we had the flood event. There was a million odd litres of water that flooded into the site on 2023.
That's right.
So there's some good little and effectively we're probably about 6 to 9 months over time. So with all of that in mind, it was a pretty good project.
Now, I've got one just quick story about shipping challenges. So because the amount of commodities moving around the world just exploded post-COVID, getting bookings on ships became quite problematic. And a lot of the stuff that we were bringing in was over length, which meant it couldn't go in containers and it had to go through a special method called roll on, roll off. But that all dried up because they were heading off to North America. And so in collaboration with the mill, we managed to be made aware of a toilet paper boat that was coming to New Zealand full of toilet paper. Everyone will remember the scramble for toilet paper. And toilet paper is very light, structural steel is very heavy. And that boat was really keen to get a product that would compensate for the lightweight of the toilet paper. So we loaded on about 1,200 tonnes. This is just raw steel, not fabricated, just beams and columns, onto this boat out of Indonesia to get it to New Zealand. That was one of the unique circumstances that arose on that project.
Well, Tony, I've got a question for you. What drove the decision to expose the diagrid structure and use it as an architectural feature?
Again, the diagrid, if we went to a standard vertical column, there'd be a lot of them. And the main driver was to get that mass off the ground, to have that glass box on the sort of the ground plane, to get that high visibility in, visibility out, and to lighten those edges. So WAM has used it on a couple of occasions, and it just helps to communicate and lessen the mass of the building, lighten that ground plane, and give much better sight lines within the building. And to be honest, the diagrid looks a lot better than the vertical column. So it's just the aesthetic look at the end of the day.
Richard, one for you. You mentioned the project involved full-scale mock-ups of key structural elements. The person asked, is this typical practice? How did these mock-ups contribute to de-risking the build and improving collaboration with a wider team?
Yeah, it's a good question. So I'd say, no, it's not typical. Most projects, the consultant industry and clients sort of understand what they're getting. This project was clearly not typical, and getting some of the architectural features that Tony just talked about right was massively important. And so that is what was de-risked through making these full-scale mock-ups. We managed to, as I mentioned earlier, trial some of the weld details that we'd developed with Becker, which were efficient weld details that brought the cost of this down. All of that cost saving obviously flows through to the university to give an overall cheaper product to them. Meant we could have trust and confidence in the delivery of those details when we got into the real event. And it also allowed Tony and their team to come and see the finish that we could achieve in reality. So taking what's on paper and really seeing that in reality, in the large scale of it, gave everybody in the design team this chance to come and have a look at it, to touch it, to talk about it. We even got Hawkins site painters out to trial a few things around paint finishes. So it really did de-risked the high-risk aspects of this job.
Oh. Another one for you, Tony, and the first comment has come from the audience, so it's not my statement. Architects often dream big, but projects face constraints. Was there a moment when collaboration with D&H Steel or Becker helped bridge that gap between vision and buildability?
Well, yes. So we obviously started the dream with Becker. So we did go, most of the design was pretty clear before we went to Fabricator and D&H, but that fine tuning, the thing that we don't know anything about is how they're going to build it, where they're going to put the tower cranes, what's the best way to weld, is that weld actually going to be ugly or not? So we did dream big, and those diagrids are the biggest diagrids that we've done. So we had an understanding going in, but that fine tuning was very, very important. So again, the devil was in the detail, and where we had the best collaborative work done was with Hawkins and D&H, just to figure out how these things are going to get delivered to site, how they're going to build, how that's going to interrupt the build process. So yeah, it was a journey, and you have to dream big, but at some stage, you aim for 100. If we get 80% of that, then we're happy. And to be honest, I think we hit 100%. Our big dreams were achieved.
Just something I'll just add into there. So being involved early on that ECI, it was getting best value, best detail on all the connection design and welding, but it also gave us a long lead in to look at de-risking program, look at smart methodologies. So by the time we actually delivered the first piece of steel, we knew this job absolutely inside out because we had time to be able to understand it and do all of that work. A more traditional tender is, it's sort of quite late in the piece from a subcontractor perspective. We get awarded a job and then we're straight into it with little time to actually stop and reflect about best design, best methodology. And so that was really fantastic about this job, and what is fantastic about early contractor involvement.
more about the process of being appointed on a ESI initially with a client and then novated by the main contractor, and how the main contractor responded to this process?
Sorry, Darren, you were muted at the beginning of that question.
Sorry, beg your pardon.
Say that again.
Can you talk more to the process of being appointed on an ESI initially with the client and then novated to the main contractor, and how the main contractor responded to this process?
Yeah, sure. So it's not the first time that's happened where we've been engaged by the client directly on an ECI, and I'll just say it was a competitive tender to start with. So there was 3 or 4 fabricators who got a very, very preliminary set of documentation, and we were all asked to tender from that. So the client there gets confidence of a sort of market competitive price. Once we'd gone through that process, we were then engaged by the university onto the ECI. That allowed us to do all this work with Becker and Wham. The university went through a process of tendering out and selecting a main contractor. We got a little bit involved in that process as well, because we had to do a fair bit of programming work in advance. And I would say, the main contractors were also brought on early as part of an ECI, which is massively important because we're just one of the sub trades only. So bringing them in early as well helped hugely. The other part was why we were brought in so early is the lead times on some structural steel, especially some larger members, can be quite.
Good idea. Oh, you've just gone silent, Richard. Oh, look, Richard, looks like we've it's either you've got delay or you've cut off, so I do apologise for hearing Richard's wisdom being cut short. So look, unfortunately, I think we've lost our speakers somewhere along the line. I can see them, but it's frozen. So, well, everybody, that probably must be the computer Lord's telling us it's time to wrap up. So I'd like to thank you all for your time, and thank you for coming into this webinar. I'd like to thank Tony and Richard for their time. Unfortunately, we've it seems to be locked people out, so there were some more questions, and unfortunately we're probably going to run out of time to ask them. So I do appreciate people sending through questions, and I do apologise for not being able to answer them all. But hopefully you've got at least some output from the presentation. So look, without any further ado, and thank you very much for your time, I'll call the webinar to an end, and everybody enjoy your rest of your day and the rest of the week, and let's hope that we can meet once again to talk about some further projects in the future. Thank you.